Good morning, everyone. My name is Davide Rastelli, and the title of this presentation is In-Orbit Testing of a Deorbiting Sail on the CubeSat Ursa Major. As you all know, CubeSats have introduced the concept of low cost into space, and the vast majority of them is placed in very low Earth orbit, and in this case, the deorbiting is not an issue, since these orbits are characterized by really fast natural re-entry time. But in the last years, the numbers of missions, CubeSat missions, characterized by higher orbits, have increased, and in this case, the re-entry, the deorbit, could be an issue. In this graph, you can see the up-to-G per G altitude history for a circular orbit with an altitude of 700 kilometers. And as you can see, the orbit occurs in more than 80 years. So, our objective was the development of the orbiting system with the following requirements. We wanted to meet the 25 years guidelines. We wanted it to be small enough to be suitable also for 1 unit CubeSats. And we wanted it to have a standalone philosophy, so in order to be independent from possible failure at system level of the CubeSat. And finally, we wanted to apply a plug-and-fly philosophy. On this purpose, we have developed Artica, which stands for Aerodynamic Re-entry Technology in CubeSat Applications. And the first prototype will be will be the payload of the Ursa Major satellite of University of Rome in the frame of CubeSat project. And this will be a 3-unit CubeSat. In this case, the sail will be a 700 by 700 millimeters square sail. And we developed the same payload also for another mission, the CSDC program, which is the Canadian Satellite Design Challenge. And there was a collaboration between the University of Bologna and Polytechnic of Montreal. Also in this case, the orbit was a circular orbit with an altitude of 700 kilometers. Here you can see a representation of the CAD model of the Ursa Major 3-unit CubeSat. And so the system is on the top, in this case. You can see here the main design drivers. So, as I already said, we wanted it to be standalone and mountable on the CubeSat. The system is composed of 3 parts that are the sail, the aerobrake sail, the electronics, and the mechanical deployment system. The surface, the exposed surface, the nominal, is about 0.5 square meters. And this is the minimum area that guarantees the re-entry in less than 25 years, so in order to be compliant with the guidelines for most of CubeSat missions. Concerning the mechanical design, the sail is stored in an aluminum box with a height of 25 millimeters. And as for the opening system, as already said, we wanted it to be totally standalone, so in order to be independent from CubeSat failures. While concerning the electronic design, it is based on an internal clock that starts a countdown after the release of the CubeSat. And in order to increase the reliability of the system, we have foreseen a redundancy on many components of the electronic. This slide presents the performances for 3 example orbits that are synchronous one, circular with an altitude of 700 kilometers, the CSDC orbit, which was also a circular orbit, polar one, 700 kilometers in altitude, and a generic orbit of 650 kilometers and an inclination of 45 degrees. So you can see in the first row the orbit lifetime, the natural one, that is over 100 years for the first 2 orbits and 62 for the third. Anyway, these values are not compliant with the guidelines, obviously. And then in the second row, you can see the nominal ratio area over mass and the simulated deorbiting time. Then what we have done was to consider the main disturbance torques in order to retrieve the average angle between the sail and the motion along the orbit. And so we retrieved the average area over mass ratio. And also in this case, we propagated the orbit in order to evaluate the orbit time. Also in this case, so with the disturbance torques, we are compliant with the guidelines of 25 years. Here you can see the apogee-perigee altitude history for the CSTC, that the orbit occurs in 8.5 years. And this is the system, the complete assembly, as used for the CSTC program. So the sail is stored in the bottom, and then on the top there is the electronics. We plan to improve the system for QB50, and so to reduce the size, have a more compact system, and furthermore we want to give the possibility to add optic systems and also solar cells. So we integrated the system on the CubeSat developed by the Student Society Polyorbit of Polytechnique of Montreal. And at first the integration should be with a structure developed by Polyorbit, but eventually they decided to buy a commercial T-unit structure by Pumpkin. And also in this case, anyway, it was possible to successfully integrate the whole satellite and perform the ground tests. Here you can see the assembly, so the structure with our system in the bottom and the final satellite. So the final part of this program, the CSTC, ended in last June with the qualification campaign, a vibration campaign that was performed at the Delft Florida laboratory in Ottawa. And we also performed a model analysis to predict the natural frequencies and the model shapes in order to make a comparison between the analysis results and the data from tests. Here you can see the test setup with two people mounted on a vibrating table. While these are the values in terms of resonant frequencies retrieved from the model analysis. The first two modes are associated with the lateral bending of the top electronics. The third mode involves the bottom of the box, and the fourth is torsional. While in these last graphs, you can see a comparison between the sine sweeps before and after random vibration. And the sine sweep was done in the range 5 to 2000 Hz with a constant amplitude of 0.3 Gs. And this is performed in order to assess possible structural alterations. You can see different cases. So in conclusion, I have presented Artica, which is a standalone deorbiting system, and it was demonstrated the feasibility to integrate it with the commercial structures. And our idea is to apply a standalone philosophy, a plug-and-fly philosophy, in order to allow the CubeSats to re-enter from orbits different from Galileo, so also above 700 kilometers. And in this way, it would be possible to increase the mission capability of the CubeSats and to fly in higher orbits. Thank you.
So do we have any questions? Yes, over here.
Hello, thank you for your presentation. I would like to ask what's the mass and volume of your standalone system?
Okay. So, the mass of the system that we have integrated for the CSDC, the entire system was about 400 grams. In this case, the height of the entire system, of the entire payload, was about 5 centimeters. But as I already said, we plan to reduce the electronics and add it more compact. So our plan is to arrive to a total height of 4 centimeters.
Okay, thank you. And I would also like to ask, you said that you wanted to be standalone. Do you plan to make the solar cells that will power up the whole system without using...
No.
Yes, or does it have to use power from satellite?
In this case, we are using only batteries. Our idea is to have batteries coupled with solar cells.
But the batteries of your own system?
Yeah, of our own system.
Thank you.
Over here.
I have a similar question. In your calculations for your deorbiting, did you assume that your system was controlled so that you could actually point the solar cell in the right direction?
Okay. No. So it would be an improvement just to reduce the number of batteries, but we have not an attitude control system to orient correctly the payload toward the sun to get the energy. If that was the question.
That was the question. So then how do you know for sure that you can deorbit in such a small time if you cannot control the direction of the cell?
Well, but we also plan to use the batteries, so that would be only a backup, let's say, the presence of the cells. Because anyway, we want to use our batteries.
No, I meant the solar cell. I mean your deployable structure.
Yes.
That deployable structure is not controlled with your system.
No, but no, it's not. It's it deploys automatically.
Yeah, and then how do you keep it? I mean, you're trying to increase the drag, right?
Yes.
So how do you keep your cell or this structure? How do you keep it?
I mean, how do you keep it once it is open?
Yeah.
Once it's open, it's the mission is over. So it exposes the surface. There's no need of energy, of batteries or power supply.
But how do you keep this surface perpendicular to your velocity vector?
It's a passive. It is stable. It's a passive stabilization.
Okay.
So along the orbit, we consider that because of the passive stabilization, the exposed surface will be maybe not the nominal one, but a surface that, but also, as I mentioned before, also if the surface is not the nominal one, if we consider the disturbance torques, as you can see in the fourth row, the average area over mass ratio still guarantees to perform the deorbiting in less than 25 years due to the passive stabilization.
So maybe you could follow up at break. I think we're going to have to move on to the next paper. Thank you very much.